Okay, an exponential function is a function where the number, or the base, is raised to a variable. Okay, in other words, we change where the variable is located. So here you can see there's our base. So there's going to be some sort of number there, and the variable is up in the exponent location. Okay, so some examples of what would be considered to be an exponential function versus stuff that's not. So f of x equals 2 to the x would be considered exponential, whereas f of x equals x squared is not. That's a quadratic. F of x equals 1/2 raised to the x power, so we can have fractional bases. Here, sort of a non-example, 1 raised to the x power. Even though the variable is in the exponent position, the base is 1. So what's 1 to any power? It's going to be 1, except at 0, in which case we have something else. But so that doesn't really count as an exponential function. Then one more example. So f of x equals 10 raised to the 3x minus 1 power. And something that I don't expect us to encounter, but if we take a variable and raise it to a variable power, that's actually not considered exponential. That's considered something else. A couple of quick reviews of exponent rules. Anything to the 0th power would be considered 1. If I take any number and raise it to the first, I get that same number, so x to the first is equal to 1. Negative exponents, so here that just means we're dealing with some sort of fraction in order to make that positive. And if I have a fraction raised to a negative exponent, what I can do then to make that a positive exponent is I can switch locations. So I can essentially look at the reciprocal of that particular statement. Okay, so let's actually take a look at a graph of just a basic exponential. So I'm just going to come up with a couple of numbers here. So -3, -2, -1, 0, 1, 2, and 3. So we'll kind of translate that. So that's 2 cubed, which is 8, 2 squared, which is 4, 1 squared, which is, 2 to the first power. I'm going to watch that. 2 to the first, which is 2. 2 to the 0, which is 1. 2 to the -1. Okay, remember your exponent rules. That's 1/2. 2 to the -2 is 1/4. And 2 to the -3 is 1/8. Alright, so then I'm just going to plot the ordered pairs that I've generated so far. So -3 and an 1/8 is barely above the line, above the x-axis. -2 1/4 is a little bit higher up, but still below, but still really close. -1/2. Yeah, still need to get a little closer there. 0, 1. That one I can do. 1, 2, 2, 3. 2, 8. 2, 4. Whoops. And 3, 8. Okay. And so if I connect all of those points, we get this very interesting shape. Sort of looks a little quadratic on one piece, but then it looks like it's getting flatter and closer to something. Let's do the same numbers with 1/2 to the x and kind of see if there's any sort of interesting pattern that we notice. So we'll do -3, -2, -1, 0, 1, 2, and 3. So here we have 1/2 to the third power, which is 1/8. 1/2 squared, which is a 4th. 1/2 to the first, which is 1/2. 1/2 to the 0, which is 1. 1/2 to the negative 1. Okay. Remember, negative puts it as a fraction, so flips it as a fraction. It's already a fraction. So if I flip 1/2, reciprocal 1/2, I end up with 2. 1/2 to the negative 2. So we already know 1/2 squared is 1/4, so that negative piece actually makes that equal to 4. And 1/2 to the negative 3 makes that equal to 8. So let's plot that. So 3, 8, negative 2, 4, negative 1, 2, 0, 1. And hopefully from here you can like, oh, I see what's going on here. Oops, make sure it curves there. It doesn't cross the x-axis because it doesn't actually physically cross. All right, well, what do you notice? They look very similar to each other, don't they? Okay, and so there's actually something else going on that we can now talk about. If you notice, the base happens to be bigger than 1 in that first example with 2 to the x, and here the base happens to be less than 1 with 1/2 to the x. And so we actually call, when it's bigger than 1, we call that a growth curve. Like in science, when you hear something called exponentially growing, your bank account is exponentially growing. And when it's less than 1, we refer to that as a decay curve. So let's take another look at these graphs then, and let's see if we can identify some characteristics of them. Starting with domain and range. So in 2 to the x, you can kind of see that there's really no limiting value on x's. Any x I can come up with, I'm going to be able to find an ordered pair that has that x value in it. So there's no restrictions on x. However, what about the range? And kind of think about it for a second. Is there any way that I can get a negative y value out of this? Is there any way I can get a y value of 0, as a matter of fact? So the answer being no, so it is bounded by 0. So then it's not included, it's excluded value. So we put a parenthesis on the range with the 0 out to infinity. What about an x-intercept? In this case it does not cross. So there is none. What about a y-intercept? Okay, crosses at 0, 1. And graphically, what do we call that when I have sort of this line that is sort of draw a line in the sand? It doesn't actually cross the x-axis at all. And so that's what we refer to as an asymptote. And that has the equation of y equals 0. Okay, let's go to the 1/2 to the x and see how that compares. Domain, no restrictions on it. Range has still got that, again, that asymptote at 0 that we can see. So it's going to be bounded by 0 out to infinity. There are no x-intercepts, and then oddly enough it crosses at 0, 1, and it also has an asymptote at y equals 0. Again, you kind of think that there's this imaginary line that we have right at the x-axis that we are not going to cross. Something to think about as we look at the two, look at all these properties and characteristics of it. Even though the bases are different and the graphs are different, there seems to be some very strong similarities between them. And actually, if you want to take a second and pause the video, see if you can identify what are some commonalities. What do they have exactly in common, or what kind of patterns can you notice in looking off the graphs and looking at the ordered pairs? Okay, notice that all 5 characteristics are the exact same, that all the domain, range, intercepts, all of those match. And more on top of that, do you notice that if we look right around -1 and 1, there's some very strong commonalities going on there. And you kind of see the same ordered pairs on both pictures just slightly reversed orders, but you still see the same ordered pairs. So what we can do is we can generalize this to identify some very specific characteristics that all exponential functions have in common. First and foremost, they all go through the ordered pair 0, 1. Then they all, again this is in general in terms of any given base, they all go through the ordered pair 1, b, and they all go through the ordered pair -1, 1 over b. So any base I have, I can automatically plot 3 ordered pairs, and I'll even go one further and say there's always going to be an asymptote of x equals 0. Okay, and so with all those facts in mind, instead of having a single parent function, we actually have a family or a class of parent functions given exponentials and connected to whatever the base is. So once I know the base, then I can write the ordered pairs that are unique to that particular parent graph. Okay, so the nice thing is we can use our transformation rules to sketch different graphs of these things. So for example, if I am adding something on the outside, that means I'm going to add something to the y value. If I'm subtracting something on the outside, that means I'm going to subtract on the y value. If I'm looking on the inside here, remember inside is opposite of what we see. So I'm going to, even though it says plus c on the inside, it means I'm really going to subtract c from the inside, or from x. And again, if it says minus c, I'm really going to add c to x. Reflections. Okay, if the negative is on the outside, what does the outside change? That changes y values. If it's on the inside of the function, that changes x values. And if we are multiplying, in both cases we're multiplying on the outside. So that would mean we are going to multiply the y values by whatever that number is. And we actually have terms for this, so let me kind of remind us. So if that constant is bigger than 1, we call that a stretch. And if it's something smaller than 1, between a positive number between 0 and 1, we call that a compress. The negative actually creates a reflection. Okay. All right. Another word of caution. This is sort of a huge mistake that I see on something like this. So take a second, pause the video. If I asked you to evaluate 2 in that, take a second, think about what would you get, and I'll kind of show you what the biggest mistake that I see with this is. Okay, I have a lot of students that will do this to me. They will multiply the 2 and the 3, and they'll say, oh, it's 6 to the x. Now, let me show you what happens if we evaluate this using order of ops. Do a little question mark for just a second. Okay, now I know 6 squared is 36. Now 3 squared is 9. 2 times 9 is 18. Those don't match. Okay, so be very careful when you have multiple transformations. So if you have more than one transformation, you want to use order of operations. Or Pemdas to determine what to do next. Order of ops, by the way, in this case, in this example, you get parentheses and then multiply. Parentheses come first, not multiply comes first, which is why the mistake typically shows up.